So this video is looking at molecules with octahedral electron geometry. So octahedral electron geometry is in the case where you have, say, something like this. Well, sulfur has 6 electrons, fluorine has 7 electrons, but then times 6. So I've got a total of 48 electrons to place. I put sulfur in the middle, and I bond it to all my fluorines. Okay, and then I put my lone pairs all around it. And as we can see now, I have a total of 48 electrons placed. My bond pairs is 6, my lone pairs is 0, my total pairs is 6, and my general formula is AX6. Now the electronic geometry, as we can see just by the title of this right here, is octahedral. Okay, and I'm going to put my A in the middle right here. And how would we arrange these to minimize the repulsions between all the electron pairs? Well, I'll have 4 in basically a square base right here. Okay, it forms a square base. Then I have 1 coming above and 1 coming below. This arrangement minimizes all the repulsions between the bond pairs. And that right there minimizes, it allows for 90 degrees of separation between each of the pairs of electrons. So I do sulfur over here, and then I do fluorine up here. Okay, same arrangement. So hopefully you can see that there is a square base and that there is a fluorine above and below it. This one is still, again, octahedral. And all my bond angles here are 90 degrees. So all along the square plane. So hopefully you can see that there's like a square plane right here. All of those bond angles are 90 degrees. Okay, and then there's also 90 degrees from the fluorine above the plane to the plane. Okay. BRF5, if we go and draw that out, we'll have bromine in the middle, bonded to 5 fluorines. Okay, and with 5 fluorines, that leaves us with 2 electrons left right at the end. If we have 2 electrons left right at the end, they have to go in the central atom. So I have 5 bond pairs, 1 lone pair for a total of 6, and I have AX5E. Now, in this case right here, it doesn't really matter where you put the lone pair, but typically we put it below the plane initially. Although you could actually orient this in any direction and it would actually still work. If you put the lone pair anywhere else, it would still create the same shape. So we put our lone pair down here. Okay. And what this does, again, the electron geometry is preserved, it's octahedral. But what effectively this does is it doesn't change the bond angles on the plane. Where it does change the bond angles is from this fluorine here and the plane itself. So this angle becomes less than 90 degrees. These are preserved at 90 degrees. And that's because this right here, this lone pair, pushes down on all of these, but it doesn't squeeze them closer together, right? It pushes these 4 X's, these 4 surrounding atoms, towards this atom up here, but it doesn't squeeze them close together. So this stays at 90 degrees. Hopefully you can kind of picture what type of shape this makes. Again, we've got a square base here, okay, coming up to a point right here. Okay, well, a square base and a point. That right there is called square base pyramid. The last one that we're going to take a look at is xenon tetrafluoride. And you might be thinking, well, how do I do this one? Because xenon does not have like much reactivity because it's a noble gas. Well, under extreme conditions and reacting with fluorine, xenon can react and form compounds. And so xenon tetrafluoride looks as follows. It's got a xenon in the middle. It's got fluorine over here, each with the correct number of lone pairs on the surrounding atoms. All right, so all my fluorines have their octet. And then over here, I've got 2 lone pairs. So now I have a total of 4 bond pairs, 2 lone pairs, 6 AX, 4E2. When we go to place our next set of lone pairs, I already have one on the bottom. So let me just draw that, okay? I've got one on the bottom. Where would I place this other lone pair to really minimize those repulsions? Because remember, lone pair repulsions are very strong. Well, the only other place I could put it is at the top, right? And that'll minimize the repulsions between these lone pairs. Now, I'm still going to get repulsions between the lone pairs and the surrounding atoms, but I have now avoided placing these lone pairs together, so that actually is more energetically stable, right? Again, still octahedral, but as you can see, we have effectively just this like square plane of atoms, right? With lone pairs above and below. No bond angles are affected. This is still 90 degrees, okay? And yes, you could in fact draw this in this manner right here, right? But it's typically drawn this way to show that it comes from an octahedral orientation. This is called square planar. Okay, and what we don't have drawn here is the lone pair here and the lone pair here. Got our bond angle of 90 degrees, right? And that completes VSPER. That's all the various molecular geometries that can come from octahedral.